Welcome back to our lesson in nomenclature. And before we begin, I want to make sure that you have the right tools. What we have out in front of us is our note pack. And let me just kind of bring up my image of the note pack. The last time we were together, we had just finished talking about how atoms arrange themselves on the periodic table and had drawn some practice models of phosphorus and potassium. The next blank spot we have is actually on the bottom of page 5. So before you begin listening to this video instruction, be sure that you are on the bottom of page 5 of our note pack. And another good tool to have out is our periodic table. All right, so our periodic table along with the bottom of page 5 in the note pack. And what we'll continue to do then is pull up our PowerPoint and begin talking about some words. The next step of our journey is to start taking atoms, which are very unstable in their electron arrangement, and putting them together to create compounds we call compounds are ionic or compounds are molecular. And the first part of our journey of nomenclature, learning the language of chemistry, will be creating ionic compounds. So we just have to focus on one category first, then the other. Let's take the time to write in our note pack the following vocabulary words. The first of our terms is called an ion. An ion are charged atoms. Remember, to a chemist, we only care about electrons in terms of an ordinary chemical change. It's the electrons, and more specifically, the electrons in the outermost energy level, that a chemist needs to keep track of. And the outermost electron energy level allows a chemist to predict things such as reactivity, physical characteristics, properties, and how it bonds to create a compound. Atoms are unstable in their arrangement. Every atom has an envy of the noble gases because of their full electron in the outermost energy level arrangement. And atoms are going to do whatever it takes to become like a noble gas. They will either lose electrons, gain electrons, or share electrons with other atoms to become more stable, like the noble gas. So as we begin talking about ions, these are atoms that, in order to become more stable, have either lost or gained electrons. A type of ion known as a cation is called a cation because it is positive. To help me remember that cations are positive, I notice the little positive sign right in the term cation. Cations are positive ions because they have lost electrons. Sometimes that confuses a beginning chemistry student. But if I model that, let's say with a simple atom such as lithium. Lithium, who is number 3 on the periodic table, mass number 7, just reminding us of standard notation. Draw with me, remember. Draw on these extra notes so I know you're watching the video. That would tell me there's 3 positive protons in the nucleus, and there are 4 neutral neutrons with an electron arrangement of 2 and then 1 electron. In a neutral atom, atoms are neutral, ions are charged. That's a big step forward. Atoms are neutral, that the positive protons do indeed equal the negative electrons. But that's not the case here any longer when an atom forms an ion. Remember, every atom wants to become like a noble gas. If lithium can lose an electron, now it's going somewhere, someone else wants to hook to lithium and take that electron from it and form a compound. But if we lose an electron, we still have 3 positive protons, but now we only have 2 negative electrons. 3 positives and 2 electron negatives give me a resulting charge of a positive 1. The atom of lithium is neutral. The ion of lithium carries a +1 charge by losing an electron. Remember, there's an unneutralized proton,
unaccounted for by an electron. Loss of an electron is a positive ion. And we literally write that symbol for the lithium ion as Li with a +1 as a superscript up high. Lithium ion carries a +1 charge by a loss of an electron. Please add on the extra note so I know you've been listening to the lesson. Let's talk about anions. Anions, this is my way of remembering that they are negative ions. A negative ion, the A, then the N, in my head reads a negative ion. Anions carry negative charges because they have indeed gained electrons. Now let's model something that might look like that. I'll do a fluorine off our periodic table. Look with me. Fluorine has an atomic number of 9, a mass number of 19. I'll just pick the nearest whole number. There are, of course, a variety of isotopes. Drawing that simple model of fluorine places 9 positive protons. To do the subtraction, 19 minus 9 would give us 10 neutral neutrons, a configuration of 2, then 7 electrons. Right now, this atom is very unstable. It really wants to have a full outer shell. Remember up above lithium? We said it's easier to lose one than try to put 7 in. By losing one, the outermost electron shell becomes full, just like the noble gas helium. Well, with fluorine, do you think it's easier to gain one and become like neon with 10 electrons, or try to erase 7? Lose one, or gain one or lose 7? Well, of course, fluorine was going to gain an electron. If we add an extra electron, it had 7. Let's put 8 in the outer shell, giving it 1 extra electron. 9 positive proteins, but 8 and 2 now is 10. If I have 9 positive protons, but 10 electrons, do you see how the resulting charge gives it a -1 overall? When atoms gain electrons, they become more negative. Electron particles are negative. Adding in extra negative particles makes the atom become negative. Those are known as anions. Atoms that lose electrons have unbalanced protons. Loss of an electron creates a positive ion. Cation, see the T? A positive ion. An anion, a negative ion. Loss and gain of electrons. And friends, you can start predicting a beautiful relationship between cations and anions, positive and negative, by the simple law of electricity, opposites attract, that I must have a cation and an anion electrically neutralized to form a compound. And that's the heart of ionic compound chemistry. Certain elements lose electrons, certain elements gain electrons, the heart of forming that beautiful relationship known as ionic bonding. Let's take a peek then at our next slide. Let's model a sodium and a chlorine. Now a sodium and a chlorine, give myself room to draw, makes us flip to the top of our next page. Let's draw simple models of sodium and chlorine. So this is on the top of page 6, really under the number 1 and 2. I'm just going to put them all onto the same slide. Alrighty. So first we go to work with a little periodic table skill. Do you see where sodium is? If I just bring up the periodic table quickly, sodium, of course, right here, sodium is number 11, and let's use a mass number of 23 just to draw that simple model. So here's sodium, Na, number 11. And just while we have it up, we'll find chlorine over here, number 17. We'll pick an isotope. Let's pick chlorine 35, and we'll just begin drawing simple models. I have a sodium and a chlorine. Alrighty? So I'm just kind of getting that ready as we begin drawing simple models. Standard notation for sodium would place 23 over 11. Sodium, as a simple model, has 11 positive protons, 12 neutral neutrons, and an electron configuration that places 2 electrons in the first energy level, 8 more electrons in the second energy level, and 1 valence electron in the third energy level. Remember our periodic table skills. We know the meaning of this based on where it lives. We know that because sodium lives in period 3, we knew 3 energy levels. All the elements in period 3 have 3 energy levels. That's why it lives where it lives. We also know that sodium lives in group 1A. That tells me it has 1 valence electron. The electron in the outermost energy level is the term valence. We drew 3 rings with 1 outer electron, 1 valence electron. This is very, very unstable. This outer electron shell is not a completely full shell. Every atom wants to be like a noble gas. Do you think it's easier to try to input 7 more electrons to achieve an outer shell that's full, or might it be easier to lose 1 electron, erasing that entire third energy level? Losing 1 electron makes the second energy level the outermost energy level, and it's a full outer shell. Gain 7 or lose 1? Well, I agree with you. It's easier to lose 1 electron. And that's exactly what sodium will do. It wants to lose this electron. Where would it go? Well, suppose there's another element, like chlorine. And again, just continue drawing a simple model of chlorine. You're kind of putting it down here in step number 2. A simple model of chlorine. Let's start with an atomic number 17, mass number 35. We put mass number over atomic number. It just helps me draw a simple model of a chlorine atom. We would place 17 positive protons. 35 minus 17 gives us 18 neutral neutrons. An electron configuration of 2, 8, 7. Chlorine lives in period 3, 3 energy levels. Chlorine lives in group 7A, 7 valence electrons. The number of energy levels comes from its period. The number of electrons in the outermost level comes from its group number. The representative elements, these group A's, represent their number of outer electrons by what group they live in. Well, right now, I'm noticing this outer electron, this outer energy level, the third ring, is not stable. It isn't full. Remember, every atom wants to have a noble gas arrangement, a full outer energy level. Right now, it only has 7. The third energy level requires 8 to be full. So we have a choice. Do you think it easier to put in 1 electron to complete that outer ring, or to try to lose 7 electrons and erase that whole third energy level? Gain 1 or lose 7? Well, I agree with you. It will most obviously lose, excuse me, I'll start over that. It'll gain that electron to complete the outer shell. And where it will go in is in this third energy level. We will add in the extra electron. Where do you think that would come from? If this wants to gain an electron, where might it come from? And I know you're seeing it. I know you see right here a beautiful relationship forming between a sodium and a chlorine. If sodium wants to lose 1, chlorine wants to gain 1, we start to develop what's called an ionic compound, the loss and gain of electrons. Well, let's see, what would the resulting ion be? If sodium atom loses an electron, it goes to a +1 charge. The sodium now becomes an ion with a +1 charge. I'm going to write that as the Na+1. Now remember, loss of electron creates a cation, a positive ion. The chlorine gained an electron. Gaining an electron produces an anion, a negative ion. The chlorine started neutral, but by putting in an extra electron, it now carries a -1 charge. Sodium was neutral as an atom. By loss of an electron, just one electron is lost. We still had 11 positive protons, but now with losing this electron, we only have 10, giving me a net +1 charge. Chlorine, if we input to create a total of 8, it had 7, but if it now has 8 by adding that electron in, it still had the 17 positive protons, but now a total of 18 electrons. It has a net charge of -1. When I gain electrons, it becomes negative. When I lose electrons, they become positive. And perhaps you can see when a sodium atom bonds to a chlorine atom, forming ions, we create a compound built of ions known as sodium chloride, an electrically neutral compound built from a cation and an anion. Sodium chloride is ordinary table salt. Notice how overall we've built a model that is electrically